All right, so here we are looking into three types. I mean, later on you will see one of our case studies. We are evaluating that design in three different analyses. The first one is static failure analysis. The second one is fatigue failures analysis, and the third one is buckling failures. Okay, so static, of course, is talking about usually is on the civil structures or our structure, our model itself. Is it strong enough to withstand the static loads? Okay, so static loaded structures, is it will it cause any permanent deformations? This permanent deformation basically will it cause yielding. Okay, so if it's yield, then basically we are saying that the model will fail. Right. So usually it is when we say a static load, then usually it's weight lah. The load from the caused by the what we call the weight loads itself. Okay. Those severe structures accidents when you read from the news, especially those new severe structures. Okay, is still under constructions, then you have a sudden collapse that usually is statics related failures lah. So basically, when it cannot withstand the loads that is given, I mean the material or the structure, it basically is exceeded. You have exceeded the load that has it given. Okay, induce the stress that exceeded the strength of that material itself, then it will basically cause failures. So the reason accident, I think construction accident will be the one that in mid valleys. Okay, the pedestrian bridge connecting the LRT stations to the mid valley mall. That is one is still under construction. Then a sudden failures. Okay, I mean basically the collapse of that particular bridge itself. So it's new. It's not under in operation or in service yet. So it have a sudden collapse. Then you have no external so-called external what I say external loads, okay, that induce additional stress. Then and from the ambience, from the environments like wind, strong winds or whatever is coming in, then that will be more towards static, the load itself, right? Then fatigue failures, okay, so fatigue failure is when it's subject to dynamic loads. Okay, when we say dynamic load, then it will be repeated, okay, sinusoidal, repeated, we call reverse, okay, completely reverse types of loadings coming in. Then if you're looking into over time itself, static probably let's say your P is your load itself Newton, then over time itself is statics. Right. So fatigue itself it is subject to a dynamic load, then probably your T over P. Then so you will have dynamic loads. Okay. Subject to dynamic loads, then it will cause also failure. So this failure we categorize under as fatigue failures. So it won't happen. This have to be subject to dynamic loads. I mean this type of loadings. And it won't happen immediately. So it usually go a number of cycles after the similar loading is applied to that particular system or particular structures for over repeated cycles. Okay, then it may cause, okay, it may basically give a growth of so-called cracks, okay, surface cracks, then causing the degeneration of the strength of the material. Then only you have a failure, right? So usually it have one of the criteria is it have to be dynamic loads, okay, and it won't have it won't so-called happens usually it won't happen in when it is still under construction. It have to be in service, then only you have this external loading coming in, and this external loading have to be repeated. Okay, it's a dynamic types. Okay, then and it won't immediate cause failures. Okay, it could be over times. Okay, depends on how high is your loads. So it depends on the number of cycles. Okay, so it could be 10,000, it could be 5,000. If you have a very high load giving high stress, then probably 500 cycles it could be failed. Okay, so it all depends on number of cycles. So it will create some weaknesses, okay, onto your for example the cracks, okay, onto your structure, then causing degeneration of the strength of the material. Right, so one of the example will be that if you know probably an accident in Malaysia, I mean in Penang, there is one buildings I think happened in 2000 around 13 or 11, 12, right? So that is one of the buildings. So the wall on the tops of the basically the buildings basically collapsed and hit one of the car, okay, pass by. So that day itself is you have very strong winds, okay. Then you have a very what we call there was a thunderstorm over there. So that load, we are saying that this wind itself is an external loading, okay, causing this external loading itself is causing this so-called repeated, okay, dynamic loads. So it doesn't happen. Why in this building itself is already it started in service I think 20 years ago, right? So it already been there for many years, okay, without issue. Why that day it happens? So basically it is after so many cycles, okay, then it cannot stand with it, then it basically yeah, collapse. Okay, so that is more towards fatigue failures. So it's important for us to evaluate or to investigate whether our design that we are proposing will have any issue with failures or not in terms of static, in terms of fatigues. Of course, if you have a slender materials, slender structures, okay, for example, like this, right? But then instead of your load is along this line, along here. So if you have a compression load along here, okay, along from the tops, okay. So if you have a fix here, it can deliver along from. If you have a load from top, so probably you have to consider buckling. Will it buckles? Okay. So you have it's loaded in a compression, so it may undergoes large deformations and basically will lose its ability to carry loads itself. Okay, so you have also need to take note in the case of your design itself is subject to compressions, and your design itself is a very slender structure. So, right. So we start with static failures theories. So I suppose you have go through this before, but then here we let's have a look on few theories that or criteria that we can use, okay, or available in ANSYS that we can apply, okay, to evaluate our so-called designs. Okay, so of course here we are saying that no universals, okay, it all depends on the material itself, the stress itself that we want to use. Okay, so here we basically divided into two parts. I mean ductile materials and brittle materials. Okay, two categories. Okay, because a lot of time this brittle material you have the strengths. You don't have U strength. Brittle material you straight away to ultimate or tensile strength. Then a lot of time their ultimate strength in U and ultimate strength in tension and ultimate strength in compression is different, right? So you have to look into it or evaluate it differently, okay, using different theories. So we deal with ductile material more, okay? So you have to take note on the what we call the available theories that can be applied for ductile materials. So ductile material, you have yield strength. Okay, so usually it compare our stresses, okay, with yield strength. Okay, brittle material, you don't have yield strength, you straight away fracture. So it compare our stresses induced to our ultimate strengths. Okay, so here ductile materials, brittle material, how you separate them is based on the what we call the strengths. Okay, that's one. More than 0.05, then it's categorized as ductile. Less than 0.05 is categorized as brittle behaviors. Okay, so under ductile itself, if you want, if some ductile material, you have also the yield strength. Okay, in compression and yield strength in tensions, or your tensile yield strength or your compressive yield strength, they are different. Okay? So if they are different, then you have to use this what we call column ductile column theories, right? So that is just a flow maps, okay? That basically tell you which category or which theory that is suitable, right? So if it's yes, and usually they are same, okay? If you're using steel, structural steel, they have the same compressive and the tensile yield strength, right? So then it goes to what we call here, okay, coming down to here, then you have two categories, okay, two criteria. Here is MSS, maximum shear stress, and distortion energy. All right, so here there are two, this theory, I mean, one is more conservative. Later on we'll see into these two, MSS and DE. MSS is slightly conservative, okay, compared to DE theories. Okay, so here we are saying that MSS is good if it, because it's designed, okay, it is conservative, so it is suitable for design stage. Okay, when we are doing design, we have so many unknowns, okay, because everything is new, right? So we need a more conservative theories to evaluate our so-called designs. Okay, so if you are talking about, if you want that particular structure is there already, we want to analyze. Okay, so we will want to evaluate failures that close to the more to actual conditions. Okay, so then analysis wise, you have to use a less conservative theory, which is DE theory. So later on we'll look into this, right? Then if it's difference, then different strength, use strength in tensile, tension and compression, then you have to use column mole. So these column moles also happen to have in brittle materials, that way you can use it. All right. So under brittle material, we have this maximum normal stress, MNS, right? Then we have a brittle column mole, and we have the modified moles. Okay, so where brittle, the maximum normal stress is the most generous one that you can use to evaluate what we call brittle materials. So comparing your normal stress, maximum normal stress, or what we call principal stress with the ultimate strength straight away, right? So brittle column mole is slightly conservative, more conservative compared to modified mole. So in terms of conservative, MNS followed by modified mole, then followed by so-called brittle column mole. Okay, so that is in general, okay, the overview of what we have. All right. Then we look into MSS first, okay, the very common theory that we can use, especially you are in the design stage, then yeah, you can use MSS. So MSS say that yielding begins, okay, when yields or when static failures happens, okay, when the maximum shear stress, okay, tau max, your maximum shear stress, tau max, okay, in the stress element exceed the maximum shear stress in a tension test, okay, your tensile test specimen at the same time. So meaning to that is your when this shear stress of the stress element itself or the material itself exceeded, okay, the maximum shear stress is during your experimentals, okay, tensile test, okay. So if you are having your maximum when you are doing tensile test, right? So you have a specimen, then you pull it, right, until it fail, right? So that maximum shear stress happen at the, because this is what we call your normal stress, right? So this maximum shear stress when it fail in the tensile test specimen is when you have your sigma, which is normal stress equals to maximum stuff. When it fail, that 10 maximum itself is actually sigma over 2. Okay, so that is happen when sigma over 2. Right. So at U, okay, at U, of course, your shear, your U strength is actually your this sigma, right? When it causes failures, right? So it's U. So here maximum shear stress is U strength over 2. Okay, so we can say that is SY over 2. So here we are saying that yielding or the static failure will happen, okay, when the maximum shear stress, okay, exceed U strength over 2. Okay, so that is its theory. So what it means here, if you have a more circles, basically you have to go back to what you have learned in mechanics of materials. So I will just quickly go through it. So if you have a stress element, so if you are using a Mole circle itself, if you still remember under what we call two-dimensional 2D. So if you have a Mole circle, so this is your maximum, this is your minimum. Oops. On. This is your minimum. All right. Then here will be your R is your tau max. Okay. So tau max itself is our maximum minus minimum divided by 2. Okay. So this maximum and minimum is our maximum normal stress, or we call it at maximum principal stress. Okay. The principal stresses, the maximum principal stress and minimum principal stress. So this is related to the normal stress. So if you can find sigma 1 minus sigma 3 divided by 2, that is our tau max. Or if you can have the R itself, you can also find the tau max. Okay, then from the tau max itself, you can find your comparing with the U strength divided by 2, then you can find whether it will fail or not. Okay, so if you compare the tau max, okay, from the R itself, right, comparing with your U strength, okay, if it's more than SY over 2, your U strength divided by 2, then static failure is likely to happen. Okay, so if you incorporate the factor of safety, right, so basically it's tau max equals to SY over 2, okay, or N SY over 2 over tau max. So what it means here, so if your tau max larger than SY over 2, meaning your N is lesser than 1, then failures. Okay, in general, N larger than 1, no failures. Okay, so that is how you using safety factors or factor of safety to evaluate our designs. Of course, you can set a higher safety factors, but then in general, that is how it comes. So if your tau max below your SY over 2, meaning you have a positive, more than so-called more than one factor of safety, then meaning no failures will happen. Okay, so that is using tau max. So in the case of you are using its principal stress itself, then you have to use maximum minus minimum. Okay, sigma 1 minus sigma 3, then larger than SY, or sigma 1 incorporating factor of safety sigma 1 minus sigma 3 equals to SY over N. So SY equals to N equals to SY over sigma 1 minus sigma 3. All right, so that is the difference between our maximum and minimum normal stress or principal stresses. All right, so that is the theory of MSS. So if you having what we call plane stress, then it's still the same. If you are under plane stress itself, then you have one of your so-called one of your principal stress in 3 directionals. So one of it is 0 in that case. Okay, So you have 1, 0 principal stress, and the other 2 is non-zero principal stress in plane stress state. All right. So here it will go into 3 conditions where your sigma A, sigma B is larger than 0. So basically you have this. So you have your so-called sigma A, then you have sigma B. All right. Right. So then when we said sigma A, sigma B, then basically this sigma A is our sigma 1, sigma B is our sigma 2, because we are fulfilling this sigma 1 larger than sigma 2, larger than sigma 3. So our sigma 3 here is 0, all right, in this case. So if we are having another case in plane stress, it could be in between like this. So we have our sigma A, sigma B, right? So here we have another one is somewhere here is 0. So this is our sigma 1, sigma 2, and this is our sigma 3. So that is another case. Another one is basically happen in this, okay? Both are negative. So we have our sigma 1, sigma 2, sigma 3, which is sigma A, sigma B. So we have 3 conditions if we in terms of plane state. So it can be further lah. Basically, if you have, if we in 3-dimensional, we know that, okay. In 3-dimensional, we know that if you have 3-dimensional something like this, okay. So you have 2 more circles. So you have sigma 1, sigma 2, sigma 3, something like that, right? So is sigma 1 minus sigma 3 divided by 2, your principal stress. So in this case, we say that sigma 3, for this first case, sigma 3 equal to 0. So our sigma 1 is sigma A. Then that equation 5.1 just now is a sigma 1 minus sigma 3 larger than Sy, right? So basically now it becomes sigma A larger than Sy. For the second case, of course, sigma 1 is sigma A, sigma 3 is sigma B, then we have sigma A minus sigma B larger than Sy. So for the third case, sigma 1 is 0, as just now we have obtained. So that sigma 1 is 0, right? So in this case, we have only sigma B equals to negative Sy. So if you plot this, so this basically gives us, we plot sigma B versus sigma A, using these 3 cases, that give us, okay, what we call the graph, as you see here. Whatever inside this envelope itself is predicted safe. So if you found that your sigma A is sigma B together, okay, when sigma A, sigma B within this particular envelope itself, within this particular region itself, okay, then that is safe. All right. Then we compare back to experimental data, the actual test data, okay, when it failed, okay. So you can find out that when you compare to this experimental data, it is conservative. What it means here, all fail, okay, meaning these data are all failed data, right? So it has a very good predictions, okay, but it's far away from that particular line, because we are saying that this is our line itself, right? So anything be inside here, okay, anything inside here, no fail, okay, anything outside here is fail, but there is a gap between this, you see, there is a gap between these two. So here it's still far away from that, it's not close to, because we are saying that this line is giving failures, right? So but our failure actually happened slightly away from this particular line. So here we are saying that it's conservative all quadrant. So it's good for design. So when you have so many uncertainties, everything is new, okay, you do not have any idea or when failure will happen, and very uncertain, okay. So probably this MSS is good because it can predict, okay, failures, okay, far earlier, okay, than the actuals, okay, because it's far away, a little bit far away from the actual. Meaning, whatever we say that whatever at here, 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 if your stress happen at here, all safe, right? But in actual, when happen in actual is actually it happened at when your stress is at a slightly larger numbers, only it will fail. So it's what we call conservative. All right. So that is MSS. Next is DE theories. So we are looking into the second one is DE theory. We say that is compared to MSS is not that conservative. So what is DE theory? So DE theory basically saying that yielding, okay, or static failures occur when your distortion strain energies, your distortion strain energy per unit volume reach the distortion strain energy for you, okay, in a simple your experimental test. So what is distortion energy? So if you have a triaxial stresses, sigma 1, sigma 2, sigma 3, your principal stresses, okay, it can be split into hydrostatic or average stresses plus your distortional components or distortional stresses. So what it means here, your distortional component basically is your triaxial stresses minus average stresses or hydrostatic component, right? So that give you what we call equivalent stress. So if you are using this distortion energy theories, okay, it lead us to our stress is sigma primes. Okay, so this sigma prime basically is involving whatever your triaxial stresses, principal stresses in this case. Okay, the difference between the triaxial stresses and the average stresses, then to get these equivalent stresses, or what we call here in a more general or more common term is Volumizer stresses. Right. So here you see that our last case study we use Volumizer stress. So why we use Volumizer stress? So it is more suitable. Later on, you will see that more suitable for analysis. Okay. If you are in design, probably you have to use the tau max or your principal stresses, okay? Sigma maximum principal stresses and minimum principal stresses. Okay? So here we are using Volumizer stress. So this distortion energy will lead to Volumizer stress. So that is in 3D. In 2D, plane stress itself, then one of your sigma principal stress is 0, right? So it will only have two principal stresses, non-zero principal stresses. So here we are referring to A and B. So this will be simplified to this in 2D. So if you do not, because these principal stresses, it have to be transformed from the what we call your XYZ component stresses, your state of stress. So if you have sigma X, sigma Y, sigma Z, tau XY, tau YZ, tau ZX that you have previously, right? Then we have in originally, we have this XYZ stress component. Then we find our sigma 1, sigma 2, sigma 3, okay, using stress transformations technique. Right? So that is where you have your mole circle coming in, right? So this sigma 1, sigma 2, sigma 3 is what we have. Our sigma 1 is our maximum principal stress, or what we call maximum normal stress of this set of stress elements, right? At the same time, we also can get tau max from the mole circle or stress transformation. We have sigma 1, sigma 2, sigma 3, tau max, and their respective planes. Okay, this is what we have learned in mechanics of material. So in the case of you do not have the principal stress and you don't want to transform it, then probably you can directly use your sigma x in terms of XYZ component. You can find your equivalent stress also from in under plane or three-dimensional. Okay, you also can just substitute into this equation to find your equivalent stress. All right. So how we get this equivalent stress? So looking into the theory itself, I mean, we just quickly go through it. And hydrostatic stress is the average of basically it's average, right? So it's our average of our principal stress. So we have sigma 1, sigma 2, sigma 3 divided by 3 is our average stress. Okay, so that's done, the first one. Then look into the strain energy per unit volumes from that axial stresses, the strain energy. Then we have the distortion strain energy. We have the hydrostatics, okay, strain energies. Right, so that is related to average. So the strain energy, we look into the strain energy first. Okay, this strain energy, if you still remember when we are doing energy methods, right? We have our strain energy is 1/2 epsilon sigma, right? Then in 3-dimensional last week or 2-dimensional, we come in with 3 components, right? So that is what we have discussed. So if we know that the strains in one direction is also caused by another 2 directions. We have a positive strain caused by the same direction. We have a negative strain caused by the other 2 principal directions. Okay, so that basically, if you substitute these relations, right, into our strain itself, then we will have our strain energy in terms of the stress is something like this. All right, in 3 directions. Okay, so if you have strain energy in this case, then our strain energy by volume change, or what we call the hydrostatics, so-called stresses itself, that will be using this. So our sigma 1, sigma 2, sigma 3, or substitute by average itself, that basically give us this. The strains energy itself now become this. Okay, for average. Okay, so if you have your average square average, just now we have sigma 1 plus sigma 2 plus sigma 3 divided by 3, right? So substitute into this itself, then it will give us our so-called hydrostatics, okay, and strain energies, okay. So now we know that our distortion strain energies, okay, is equals to our strain energy minus the volumes change strain energies, or what we call the hydrostatic components. So basically, this B, okay, minus our UV, right? So that gives us UD, the distortion strain energy. So this is what we have, the distortion strain energies. Right? So this particular part itself. So the tensile test basically tells us that it U at when your maximums, okay, equals to U. Okay, so this is sigma 1 when sigma 1 equals to U. Okay, so then this thing, so sigma 2, sigma 3 is 0, right? So when sigma 1 equal to 0, U, then it failed. Okay, so then I can actually replace this sigma 1 equals to Sy, the rest is 0. So this itself now can reduce to this. Okay, so you can actually see that getting this theory itself is this equals to this. Okay. Okay, so if this is larger than this itself, then failure will happen. Okay, so in other words, the square root of these components larger than your U strength, then failure will happen. So this itself is our equivalent stress. Okay, so equivalent stress or Volumizer stress is what you have seen from here itself. How it comes is from your strain distortion strain energy itself. Okay, so larger than your Sy, then we fail. So basically, for distortion energy, for MSS itself, we compare our tau max, okay, with our Sy over 2. For DE theory, we compare our equivalent stress directly with our Sy, U strength. Okay, so that is in 3D, 2D. Okay, this is in 3D. If you are using XYZ component, then this is in 2D. All right. So looking into that, okay. So this distortion energy failure basically simply compare your Volumizer stress or your equivalent stress to U strength. That's it. Okay. So if you incorporate this factor of safety, then basically N equals to SY with equivalent stress. So it's very direct. So if you have your equivalent stress comparing with your U strength, okay? So if your equivalent stress is larger than your U strength, your N is lesser than 1, okay? If your equivalent stress larger than your U strength, and then we say that failure is likely to happen. So if your U strength, your equivalent strength, equivalent stress lesser than your U strength, then N larger than 1, so failure is not likely to happen. All right, so that is straightforward. So this is about DE theories. So if you plot this particular curve itself, comparing back to the experimental data, so you can actually see that a lot of failures data, the actual failure data, actually fall along our distortion energy line, right? So meaning to that, in terms of predictions, okay, of failures, distortion energy is closer to our actual failure data, right? So here we are saying that if you are going for analysis, right? If you want to analyze, okay, uh, uh, why it fails, or why whether it will fail or not, these things, this type of work, then probably DE will be more suitable, because you can predict your failures or simulate your failures closer to your actual failures, right? Whereas MSS theory, okay, it basically slightly more conservative, okay, it predict failures earlier, okay, happen earlier, or smaller values of sigma, or your normal principal stresses, okay, compared to our so-called DE theories. So analysis, DE theory, design, and we need conservative, more conservative theories than we use MSS. All right. So if you have a difference compressive strength and tensile strength, then we have to use column moles. So then either it is a ductile material or brittle material, so you also can use column mole. So basically, it compare your sigma 1 with tension, sigma 3 with your minimum principal stress with your compressive strength, okay, the difference between them, then compare with the factor of safety. Okay, so if you have ductile material, then it's U strength, tensile and compressive U strength. If you are using brittle material, then it's tensile and compressive ultimate strengths. All right, so so when you talk about maximum normal stress theory, right? So also the same lah. So is for brittle materials, maximum normal stress theory. So you are comparing your maximum so-called principal stress, okay, with your strength, ultimate strength in this case. So sigma 1 larger than ultimate strength, then failure will happen. Or your sigma 3 lesser than your negative compressive strength, then it will so-called failure will happen. Right? So that is a maximum normal stress theory. So how to select failures criteria? So first, of course, we have to categorize either it's a ductile or brittle material that we are using. Okay, if you're not sure, then look into the strain itself, whether it is larger than 0.05 or lesser than 0.05. So if it's ductile, you use MSS or DE lah, right? In general, okay, MSS is conservative, so use suitable for design, or you need a high reliability. So, okay, you don't want the failures happen on your design itself, you are not sure or uncertain, then you need a high reliability, then yeah, you can use MSS. DE is a typical one, so it's quite common, used for analysis. So under here, that's why we are always finding the equivalent stress, or what we call Volumizer stress, because later on we would want to use our DE theories to evaluate failures. Okay, DE is typical because it's used for analysis, because it shows a very good agreement with the experimental data, right? With the actual failures there. Okay. So if you have a different strength in tensions and in compressions, then you can use ductile column modes. Okay, for brittle and more maximum normal stress can be used. Okay, else you can use either you use this maximum normal stress, else you use column mode or modified modes. Okay, right. So that is about the what we call the criteria, right, of static failures. This is about static failures lah. Then fatigues. Okay, again fatigue it have to be compare. Okay, you have to find uh, whether we know that if only fatigue will only happen after a certain number of cycles. Okay, just now we have discussed it. So a lot of times this fatigue failure you have to refer to its material SN curve or SN diagrams. Okay, the strength, the fatigue strength over the number of cycles. Okay, so this so-called SN diagram itself basically it was plotted experimentally under a completely reverse stress. Okay, at a different stress levels. Okay, this material subject to a different stress level. Then depend and see how many cycle this material can sustain. Okay, then you can see that it plots at different stress levels. Then it sustain let's say like this 10 power 1, 10 power of 2. Then basically it tell you how many cycle that particular material will sustain at different level of this stress, right? Then it gives us a plot like this, right? So if you for steel itself, you will see that is a knee happen when it come here, then it will go like this. Okay, that is a knee of flats. Okay, over here. So this knee itself, this particular knee, when it is going to flat, and the corresponding so-called strength itself, we call it as endurance limits. So what this endurance limit means, okay, stress below any below this SE, this is your endurance limit. Anything below this SE itself, okay, any stress below this will not have fatigues. So if you don't have fatigue, so we are say that they are safe, it's safe, and you have an infinite life. Okay, so that is basically you won't have failures, meaning you have an infinite life lah, this material itself. Okay, so if your strength or your stress is in between 10 power 3 to 10 power 6 cycles. So if your strength happen at this is 10 power 3, 10 power 3 and 10 power 6. So around this region. So if your stress happen at here, right? So here we are saying that you have a high cycle fatigue. So in this case, if you have this level of stress at here, at these regions, then we are saying that fatigue is likely to happen. Okay, then if fatigue is likely to happen, here we categorize high cycle fatigues. So we need to predict its life. So here it have a finite life. So it have a number of cycle to fail, where we have to usually we have to determine the end. Okay, so here, so you from here you can predict, okay, what is, let's say from here we have this stress itself, then you can predict, okay, that particular stress, particular number of cycles is around 10 power 4 to 10 power 5 cycles. Okay, it will have failures. So if it's further to that, okay, you have even higher stress, okay, from let's say this onward to here, okay, these regions, the stress is in this region, then we are saying that is a low cycle fatigues. Below 10 power 3 is low cycle fatigue. So usually you will still have fatigue, but then before the fatigue happens, you already happened. Static failure already happened, because usually your stress, this stress, this stress at let's say 700 megapascal, usually is already exceeding your U strength. Okay, your U strength. All right, so it's already exceeding your U strength, then static failure will happen first in low cycle fatigue. So here we are focusing more towards high cycle fatigues, 10 power 3 to 10 power 6 usually. All right, So for steel, okay, so if you want to know whether it will fail or not fail in terms of fatigue, first we have to know the endurance limits, right? For steel particularly, okay. So how to determine our endurance limits? First, you have if for steel itself, the endurance limits is determines, okay, by its ultimate strength. So if your ultimate strength less than 1,400 megapascal, then you can basically you can multiply with 0.5. Half of your ultimate strength is your endurance limits. It's larger than it is 700s, right? So that is from experimental. They found that endurance limits for steel is something like this. So only for steel, metals related, then only you have ferrous metals. You have endurance limits. Non-ferrous metals like aluminum, you do not have endurance limits. So basically, you won't see something like flat like this, but you will see your SN curve basically will go like that. So, okay, you don't have a flat going flat like that. So that is for usually aluminums, non-ferrous metal. All right. So first thing we have to evaluate whether it will have fatigue or not. First, we have to know the limits, the endurance limits. The second things we have to know is this stress, okay? Whatever the stress that giving us that we found is a static stress, then no, it won't have fatigue. So it have to be dynamic or fluctuating stress. Okay? So it have to be fluctuating stress. So we have to categorize this fluctuating stress. So if you have a dynamic load, it will induce this dynamic stress, okay, or what we call fluctuating stress. So fluctuating stresses often is a sinusoidal patterns because of new to the nature of your dynamic loads caused by rotating machineries. So usually it is dynamic. So it is the sinusoidal. Okay. So if you have a dynamic loads, if this is your F load or P, then it will give you the stress also dynamic. Right? So the peak, usually we want to know the peaks. There are, it could be a lot of different shapes, but then the peak itself is more important. Right? This peak itself, what is the peak? So we can categorize terms, okay, in terms of it mid-range as well as alternating. So it's steady component or mid-range components where it starts, and alternating component where is the peaks. Okay, so if you are looking into a sine wave like this, sinusoidal function like this itself is your this is sigma, this is your t, or this is your or f t. So this is your a, okay, alternating peak. So the mid range or what we call steady component is half of this, okay, which is happen at here, sigma m. All right, so it happened at this particular point. This happened at this particular point. So it could be sigma m or sigma fm. Okay. So if we're saying that, okay, our fm or mid-range force or load is maximum plus minimum divided by 2 lah. Right. If I want to find our alternating force, then it's f max minus f min divided by 2. So it's absolute values. Right. So general fluctuating, okay, if you're looking into this graph itself, general fluctuating stresses or force, then you have a sinusoidal functions, then it could happen at anywhere. Okay, so this line itself is our sigma m mid range. Okay, so what to get our sigma m is maximums. Okay, this is our maximum plus minimums. Okay, divide by 2. Right, so it's happened at here. Maximum, our alternating is maximum minus minimum divided by 2. So it's maximum minus minimum, okay, divide by, is getting this, right? Divide by 2, then we are getting this, half of it. So that is our alternating, right? So that, why we need all this, because the theory itself later on, you can see that we need to determine our sigma m, sigma a, our endurance limits before we can evaluate whether you have fatigue failures or not. All right. So this sigma m, sigma a, and also SE will define in our we need to be determined before we can define whether there is a fatigue failure when we want to apply the different theories, okay, or different fatigue failures theories. So if you have the SN curve itself, then this usually is this stress itself is a completely reverse stress. Your sigma A, then sigma M is usually 0. Sigma A compare with our compare into this number of SN curve itself. Then if I have a sigma A is 500, so you put your 500 at here, then you know that, okay, yeah, where is my N? So whether my fatigue will happen or not. Okay, so that is purely based on your SN curve, right? So we have theories, okay. Later on, you will see that we use different theories there are also theories to determine fatigue failure, or rather than just looking into SN curve, right? So NCs itself also have this. So that is general fluctuating stress. So repeated stress, basically, you have a minimum equal to 0. When you have a minimum equal to 0, we call it a repeated stress. So if you have your sigma M equal to 0, okay, that is where we have your completely reverse stress. So this is very common. So this completely reverse stress is used experimentally to determine our SN curve that I mentioned to you. Okay, so this is caused by these are tabulated or come out by when you have a completely reverse stress, okay, which is your stress is like this, sigma M equal to 0. So the first one at here smaller, then you can go higher. So but is same. Both sides is same. Okay, this is same with this, but at a higher amplitude. Okay, so that is a completely reverse when a sigma M equal to 0 mid-range. Okay, so this completely reverse stress is used to determine our SN curve. All right, so if you have a difference, because that is ideal. So in actual, you could have your sigma M is non-zero. Okay, so then can I still use our SN curve, okay, to predict failures? Okay, so if no, then probably we can use theories. Okay, the fatigue failure criteria for fluctuating stress. So if your stress is not completely reversed, then probably you can use different theories to determine your factor of safety. Again, your N is larger than 1, then no fatigue. If your N lesser than 1, then you have a likely happens fatigue. So the most common, I think, is if you remember, is modified Goodman's. So sigma A over, basically comparing your sigma A, the total of your sigma A, the ratio of sigma A, alternating with your endurance limits and your mid-range stress with your ultimate stress. Okay, the total of them is equal to 1 over N. Okay, this soldier is also there, okay, but it is comparing your use strength instead of ultimate strength. All right. So this basically Langer is basically, if you see that, it is quite similar to your use what we call our static failures. So in terms of static failures, this thing sigma M is or complete reverse. Your sigma M is complete reverse, or your sigma M is 0, right? Your sigma M 0. Then basically comparing your peak equals to SY over N, right? So this is what we have our static, similar as static, right? So these are different theory that available, so okay, quite common to use. So modified Goodman is the most common, so you can use it. All right, so in the case if we find, okay, if we found that our N is larger than 1, no fatigues, so life will be what we call infinite life, right? So we do not need to predict how many cycles before it can reach before you have fatigue failures. But in the case of N lesser than 1, then we are saying that fatigues is likely to happen. So we have a finite life and we need to predict the life number of cycles, right? So if you are from SN curve itself, then you see that it is a completely reverse stress. So how to predict this, what we call is for complete reverse stress. So how to predict this N if you have failures, okay? If I have a fluctuating stress where sigma M is non-zero, right? So I have fluctuating stress, then SN curve is not suitable. So we have to basically uh, do some additional calculations, okay? Converting our stress, okay, into a complete reverse stress, okay? With the sigma A and sigma M to complete reverse stress, then only it's suitable to refer to this particular curve. All right, so let's have a look on build some relationship from this SN curve itself. Previously, we just an introduction. So now, if we really look into that, it actually give us two points that is known. Is known 2 points that we know is here. This particular point itself, we know that uh, uh, this particular curve, okay, give a function of S f equals to a n power of b, right? A we do not know, b we do not know, but we know that when sf at this particular point itself, my ff equals to se, my endurance limits, and we know that my n is 10 power of 6, right? So this is what we know. That is the first condition. The second condition is at 10 equals to power of 3, n equals to 10 power of 3, fatigue will happen, right? So this fatigue is actually fractions of my SF is actually my fractions of my SUT. Some portions, I mean the some ratio of my SUT. So this ratio is what we call fatigue strength fractions, okay, from our ultimate strength. So it's experimental, investigated, tabulated as you see here, this curve. So if I have an ultimate strength of 700, then I know that my F is around 0.84. So it will happen, fatigues for N equals to 10 power 3, my SF is probably 0.84 times our 700s, okay? 0.84 times 700. For example, so it's 588. So meaning at 588, I have a fatigues happen at 10 power 3 cycles. Okay, so that is two relationship that we can build from this particular SN curve, right? To 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 determine the unknown A and B. We have two unknown, we need two conditions. All right, so let me show you from here. Okay, so based on this, we have the first condition is SF 10 power 6 equals to SE equals to A 10 power 6B, right? So if I use log both sides, log SE equals to log A plus B log 10 power 6. Okay, so that is my first question. The second one I have is SF 10 power 3 equals to F SUT, a fraction of my ultimate strength, equals to A 10 power 3B. Right, then I have both sides log F SUT equals to log A plus B log 10 power 3. 2. Right, using from these two equations, we can find our so-called, if you are using 1 minus 2, right, then we have negative 3b equals to log f SUT minus SE. Our b equals to negative 1 over 3 log f SUT over SE. Right? So we can find our b, unknown b, from here. Right? Then at the same time, if I have b, then I can find my a, right? So a will giving us, substitute into any equation 1 or equation 2, then we can get our a equals to f SUT square over SE. So if I looking into the SN curve itself is A and B, right? So if I have A known, B known from the what we call the endurance limits and the ultimate strength and the fractions of fatigue strength itself, right? Then I can find my A and B. So if I have my A and B, then if I know my so-called stress, okay, if I A and B, basically we are having our so-called own SN curve. So if I can determine my A and B, then I can have my SN curve, right? So from there itself, and if I know my stress, which is related to the fatigue itself, so this is my stress, completely reverse, okay? Then I can find my N, okay? Whether you feel if fatigue is likely to happen, okay? So in this case, because it's fluctuating stress, right? So we have a sigma A, sigma M is non-zero, right? So sigma M is non-zero. So, and if you are doing a SN curve, it is where sigma M is zero. So here, if you're using modified Goodman or Gerbil itself, then you can find your equivalent completely reverse stress, okay, which is your sigma reverse, completely reverse stress itself by using these formulas, okay, these two, right, to find your complete reverse. So if I have my A, if I have my B, if I have my complete reverse, then I can find my N, right? So N is if you have a complete reverse equals to A and B, our N itself is reverse over A 1 over B, right? So from there we can predict the finite what we call fatigue life, okay? All right, so that is how you predict. So only when it is needed, okay, when you have below SE or endurance limits, then infinite life, then you do not actually need to predict. We know that it's infinite life, right? But it is N, if your N's lesser than 1, okay, so you have a finite life, so you have to predict your life. So of course the direct way is SN curve of that particular material, but provided your stress is complete reverse. So if your stress is not complete reverse, then you have to find the equivalent complete reverse stress using these particular formulas, right? To find your complete reverse stress, okay, then basically you have your SN curve, okay, which is SN curve, which is your reverse stress, or your SF, okay, equals to A N power B. Okay, so this SF, because we know that is a fatigue will happen, right? So this complete reverse stress basically is our failure strength. I mean, it's similar with our fatigue strength itself, right? So then sigma or reverse or complete reverse stress equals to A N power of B, right? So from there we can predict our life, okay, in this case, okay, with the A and no B is known from how we define from here. All right, so that is where we need to predict the life, right? So that this is what we call the factor of safety, just for your reference, So if you is unsure, you are unsure of what factor of safety to use, especially for ductile material. So usually for static analysis, if you know, okay, your structure is subject to static loads and you have very high level of confidence of all the design data, then 1.25 to 2 of factor of safety is good, right? So here, instead of putting, like I said, if previously we know that from the static failure theory itself, and larger than 1, no failures, right? We are saying that. So n lesser than 1 failures. Okay. So This is what we call is if you have very high level of confidence, but in actuals, okay, we would want a higher factor of safety. In this case, for static is around 1.25 to 2, right? But in general, we know that if it's lesser than 1, failure will happen. Okay, but in this case, if you are setting your factor of safety 1.25 to 2, so meaning if my n equals to 1.5, okay, so it fulfill your design criteria, and we know that it fulfill your design criteria, and we know that no static failure will happen, right? So if it's n equals to 1 in this case, it doesn't fulfill your design criteria. Is where you need 1.25 to 2, it's 1 point, let's say 1.2, right? But it is above 1. We are based on that. It's based on your analysis. It still show that static failure is not likely to happen, but it doesn't fulfill your design criteria, which is n have to be 1.25 to 2. Okay, so that is how you set. But in terms of analysis, failure is still not likely to happen, just that it doesn't fulfill your design criteria. So because you need a higher factor safety for so-called uncertainties that you do not know. So then usually we go for higher, right? So, but we don't go too high. So over too high, then it will become over design, the whole thing. Okay. So you basically you increase a lot of things. Your costing, materials, everything will increase. So this is just a guideline. If the static loads with high confidence level, then 1.25 to 2, right? If it's dynamic loads, then your n it have to be 2 to 2.5, right? So if it's your structures, okay, undergoing dynamic load, but you are about the material properties, load, stress analysis, a lot of things you do not know, then your n, of course, you have to go higher. If you have more uncertainties, then the design factor should be go higher a little bit. So it's 2.5 to 4. So for extra safety or critical components, right, you will have to put higher safety factors. So 4 and above could be solutions. Okay, could be considered. All right, so this is about failure analysis.